Here is a program that estimates a square root. On most numbers, it finishes in a flash. Then we hand it the number 54,321, and it never stops. Not slow, never. The bug is not a typo. It is hiding in the one line that decides when to quit. And finding it teaches us how to compare numbers that can never be exactly equal. Last time we met guess and check, also called exhaustive enumeration. You have a finite set of candidates, you test each one in turn, and eventually you either find the answer or run out of candidates. The trouble is, it is all or nothing. Our old square root code could only tell you whether a number was a perfect square. Ask it for the square root of 5 and it had nothing to say because 5 is not a perfect square. An approximation method fixes that. It does not demand the exact answer or nothing. It hands you a value that is good enough. We reach for it precisely when the exact answer is out of reach because the candidate values are infinite and we cannot test them all. So what does good enough actually mean? We want a root whose square lands on x, give or take a little. Concretely, we accept a guess when the absolute value of guess squared minus x is less than some small number we call epsilon. Epsilon is the leeway we allow, the size of the target band around x. Floats are central here. The increments we add are tiny fractions, and the values we compare are floats, so we have to be careful how we compare them. We never ask are they exactly equal, we ask are they within epsilon. The algorithm has 3 steps. Step 1, start with a guess we know is too small. For a square root, start at 0. Step 2, nudge it upward by a small increment. With guess and check, we stepped by whole integers. Here, the step can be 1/2 or 1/10 or 1/10,000, whatever we choose. Adding the increment gives us a fresh guess. Step 3, check whether that fresh guess is now close enough to x. If it is, we are done. If not, we keep incrementing and checking, climbing one small step at a time until our guess squared finally slips inside the epsilon band. 2 knobs control everything, epsilon and the increment. The increment is how far we move each step. A smaller increment gives a more accurate answer because we creep up on s in finer slivers. Epsilon is how close we insist on being. A larger epsilon makes the program faster because we reach the target band sooner and stop. But larger epsilon is less accurate because the moment we are inside the band, we declare victory and stop closing in. Picture it with the square root of 5. With a loose epsilon, the first good enough guess was 1 point something. Tighten epsilon and the good enough guess became 2 point something, much nearer the true answer near 2.24. So there is always a trade-off, speed against accuracy. Here is the code. First, we initialize. The variable s is the number we want the square root of. Epsilon is how close we want to be, set to 0.01. Increment is how much we nudge each step, set to 0.0001. We keep a counter, num guesses starting at 0, and a guess also starting at 0, which we know is too small. Now the loop does all the work. In plain English, while our guess is not yet within epsilon, keep guessing. The condition is, while the absolute value of guess squared minus x is greater than or equal to epsilon, we are still too far away. Inside the loop, we make a new guess by adding the increments, so guess goes 0, then 0.0001, then 0.0002, and we bump the counter each pass. Run it on 36. We know the true answer is 6. The program reports a guess of about 5.9992, and it took 59,992 guesses. Notice it did not chase all the way to exactly 6. It stopped the instant the guess squared slipped inside the epsilon band and called that good enough. The guess count makes sense. The increment is 0.0001, which is 1/10,000, and we climbed from 0 up to almost 6. So the number of steps is roughly 6 times 10,000, about 60,000, and that is exactly the neighborhood we landed in, 59,992. A quick but important aside about loops. You might wonder why we use a while loop instead of a for loop. A for loop in Python works over a range, and the step of a range has to be a whole integer, positive or negative. Our increment is 0.0001, a float. A range cannot step by a fraction, so a for loop simply cannot do this. We need a while loop whose condition we control directly. Let us try a few more values and watch floating point peeks through. For 24, the program gives about 4.898, and the true answer is 4.899, so we are close. The square root of 2 comes back as about 1.4107, near the real 1.414. Look carefully at the guess squared in these runs and you will see ugly tails, a number that should be clean trailing off into zeros, and then a tiny crumb at the very end. That crumb is floating point error, the round-off we studied earlier piling up across tens of thousands of additions. Sometimes the crumb pushes us a hair above x, sometimes a hair below. It is harmless here, but keep it in mind. It is about to matter enormously. Now the dangerous one. We feed it 12,345. There is a brief pause while the loop runs about 1,000,000 times and then it answers. Fine. Next, we feed it 54,321. That is roughly 5 times larger, so we expect maybe 5 times the weight, a few seconds. Instead, the program just runs and never returns. Something has gone wrong, so we kill it. You stop a running program by clicking the shell and pressing Ctrl+C, or hitting the little stop square. The real question is, why did this loop never terminate? To debug, we add a print every 100,000 guesses, showing the current guess and how far guess squared still is from x. Everything else is unchanged. Watch the numbers with x equal to 54,321 and epsilon 0.01. Early on, at a guess of about 10, we are roughly 54,000 away, hopeless. At a guess of 100, we are about 44,000 away. At 120, about 40,000. At 200, about 14,000, getting warm. At 210, about 10,000, then about 6,000, then about 1,400. From a guess of about 230, we were only 1,400 away, our closest approach. But the very next print, at a guess of 240, we are about 3,000 away. We got closer and then we jump back out. From there, it only gets worse. Here is the picture. We have x fixed, with a thin epsilon band around it, drawn not to scale. The guess climbs from the left. We square it and check. Is guess squared inside the band? Early on, it is far below, so we keep stepping. Guess squared rises and approaches the band from underneath. One more step should land it inside. We take that step, but guess squared leaps clear over the band to the far side, above x. The program checks, finds we are not within epsilon, and says keep guessing. So guess climbs again, and the guess squared only sails further away. We stepped right over the target. We never told the loop what to do if that happened, so it never stops. One small addition fixes it, and it is something guess and check already did. There we said, if we have passed the reasonable range, where the value is now definitely too big, just stop. We add the same idea as a second ending condition. Everything is unchanged except the while condition. We keep looping while we are still within epsilon away, and the guess squared is still less than x. The moment guess squared passes x, that second condition fails and we break out. So either condition can end the loop. Then an if else asks why we broke out. If the absolute value of guess squared minus x is below epsilon, we succeeded and we report the square root. Otherwise, we broke because guess squared overshot x, so we report that we failed to find it. Run the fixed code on 54,321 with the increment still at 0.0001. This time it ends. It makes about 2.3 million guesses, and then prints that it failed to find the square root. That is exactly right because we already knew this increment would overshoot the band. The loop ran until guess squared finally exceeded x, then stopped and admitted defeat. We also print the last guess and its square in case the user wants them. The lesson is that the program now terminates with an honest answer. It failed instead of spinning forever. Failing fast beats running forever. We do not want to fail though. One cure is a smaller increment. Instead of adding 0.0001 each pass, we add 0.00001 10 times finer. That multiplies the work by 10. We wait maybe 10 seconds, but it finishes. Before, with the coarser increment, we made about 2.3 million guesses. Now with the finer increment, we make about 23 million guesses, 10 times as many and 10 times as slow. But this time, we do not fail. The final steps let guess squared settle inside the band instead of stepping over it. We find about 233.06864 comfortably within 0.01 of the true square root. Step back and collect the lessons. First, never compare floats with double equals. If we had demanded guess squared exactly equal to x, we will almost never hit it, and the program will be a disaster. We always test within plus or minus epsilon instead. Second, being within epsilon is not enough on its own. The exit condition can be jumped clean over as we just watched, so we add an extra condition to catch the overshoot. Third, there is a genuine trade-off. We can make the program succeed instead of fail by shrinking the increment, but it gets much slower. Or we could widen epsilon, which is faster but gives up accuracy. Speed against accuracy and which you favor depends on the job. One last thing, this whole approach is slow because it starts at 0 and crawls up one tiny step at a time, even for a number whose root is clearly large. There is a much faster way to approximate a root, and that is exactly where we go next. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.